Welcome friends and welcome to my series of video lectures on design of RCC structures. This is chapter 5, shear design of beams. The title of this video lecture is RCC 5.3, numerical problem on shear design of beams. For best video quality, watch this video on laptop or desktop with resolution set to 1080p, that is HD. The expected learning outcome from this video lecture is to design a beam for shear. The contents of this video lecture are numerical problem 5.3.1 on shear design of beams. Second, variations in the problems of shear design. We are going to make use of some key terms: shear design, critical section for shear, shear resistance of concrete, Table 19 and 20 of IS 456-2000, minimum stirrups, designed stirrups, stirrup zones, bent up bars and anchor bars. Friends, we have our best friend Smarty here with some smart tips. Write down your own notes while watching this video. Pause or rewind the video whenever required. Do solve the formative and summative assessment quizzes in the video. Friends, in the last video lecture, we have seen the design procedure and the behavior of a beam in shear. We have also studied the IS specifications regarding shear design of beams in the earlier video. Now here we apply all those concepts to a numerical problem. Let us read the statement of the problem. A simply supported beam, clear span 6 meters, has effective section of 230 mm by 500 mm with 3 bars of 20 mm diameter as tensile reinforcement. It has a total ultimate load of 70 kN per meter. Design the beam for shear. Assume M25 Fe415 grade materials. Use bent up bars. So this is the statement of the problem. We will see the diagram of the problem. If you see here, you see the L section, longitudinal cross section of the beam shown here, which is cut. This is half part of the beam. Here we see the column and here we see the load WU, which is ultimate load 70 kN meter as given in the problem. Here we see the effective depth small d, which is the distance of the top of the beam to the center of the reinforcement. So this is effective depth d, 500 mm. Then the span of the beam is 6 meters. We have to note that this is clear span. So it starts from the face of the column, inner face of the column, and extends to the other face of the column at the other end. Now here we see two cross sections. First cross section is at BB, section BB. You can see this cross section BB. Here you find the breadth of the beam as given is 230 mm and we see 3 bars of 20 mm diameter. So this is the cross section. You can say it is the cross section near the mid span of the beam and it is containing the beam tensile reinforcement. Since it is a simply supported beam carrying UDL, there will be sagging, bending and tension will be developed at the bottom due to flexure, and that is why we are getting this tensile reinforcement at the bottom of the beam. So this is the situation at cross section BB. Now we have shown another cross section, that is cross section CC. We can see here that the CC cross section is the cross section along the face of the column, along the inner face of the column. Now we will see only 2 bars at the bottom here. So what does it mean? Since you are having only 2 bars at the bottom, it means that 1 bar which was there at the center has been removed or has been taken up. If you see this diagram, you will see that the 3 bars started like this, but from this point we have got 1 bar of 20 mm diameter bent up. This angle is 45 degrees. It is bent up and continued into the support. So at top, so we can see that at bottom now only 2 bars are continued after this bar is bent up. So that is why at section CC we get only 2 bars continued. So this is the understanding of the diagram of the problem. Now, what we have been asked is design the beam for shear. The question is design the beam for shear. In the earlier video we have seen the real meaning of designing a beam for shear. The logic behind designing the beam for shear is simple. It can be put in mathematical relation like this. We should design the beam means we should provide a shear resistance VUR which should be greater than the critical shear force or the ultimate shear design shear force that we are calling as VUD. So we are getting the value of VUD due to the applied load and the beam supports and all, and that VUD value is to be resisted by our design for shear. So in design for shear we are going to provide shear resistance VUR by various ways such that our resistance will be greater than the shear force that is developed in the beam due to the design loads. Now we will proceed for step 1. So in this mathematical relation, first we calculate VUT. That means how much shear force are we supposed to resist through our shear design of beams. So we are first going to calculate VUD, that is ultimate design shear force. Now we know that the shear force for a simply supported beam having UDL is maximum at the support and its value is WL by 2. This is our usual information. But here the Indian Standard Code IS 456-2000 is allowing us to choose another section, cross section, which we are going to call critical section for shear for calculation of this VUD. Okay, so let us see what is the critical section for shear. What is the meaning of the word critical section? Critical section means the cross section of the beam at which you will calculate the value of shear force for which you will design the entire beam. So as we have studied in the earlier video in detail, the critical section AA for shear, you can see this example here. The critical section AA for shear where support offers a compressive reaction. So if a support is offering a compressive reaction on the concrete at the support, what does it mean? The support is applying an upward reaction. As we know, the reaction offered by the support will be upward and the load is acting downward. So in this zone, in this region at the support, the concrete of the beam, we can say it is subjected to a sort of compression. So the support is offering a compressive reaction. This we have discussed in detail in the earlier video. You can refer to that video for further explanation. But we can simply remember right now that whenever we are having a column under the beam, not above the beam, we have seen in that video that sometimes we can get a column above the beam. In that case, the beam is suspended from column. In that case, the column is not offering a compressive reaction, it is offering a tensile reaction. That is an opposite example. But that example is very rare. This example where the column is lying under the beam is a common example. So we will always have this column offering a reaction, compressive reaction on the concrete here. Due to that, IS code is saying you need not take the shear force at the section CC, which is WL by 2. Instead of that, take the shear force at a section AA, which is at a distance small d or effective depth from the face of the column. What will happen at AA? At AA, your shear force will be less than the shear force at CC. So IS code is allowing us a lesser value of shear force VUD because the support is offering compressive reaction. This advantage of lesser value of shear force is going to make our shear design economical. That is why we will take advantage of this provision of IS code, that we will take critical section AA for shear because the support is offering compressive reaction at a distance effective depth D, which is 500 as shown here, from the edge of support, this edge or face of the support. So let us calculate the value of shear force at this section. So by a simple formula you can calculate the value. VUD will be equal to WL by 2. This is shear force at this edge, minus you will subtract the shear due to this load for a distance D, W into D. So this formula, this we have also already studied in the earlier video also, we are applying it. So WUL by 2 minus WUD, this gives us the value of VUD. So we will substitute the values. WU, note that this is ultimate load, already given ultimate load. So we don't have to multiply that load by any load factor to make it ultimate. So this is 70 as it is, into 6 by 2, 6 meters is the span, clear span. So minus 70 into 0.5. This D, effective depth, small d. So W into D, 70 into 0.5. This 0.5 is 0.5 meters, which is actually 500 mm, which is the value of D, small d. Because we want to observe the units properly, we have to convert that effective depth D 500 to 0.5 meters. So this equation will finally lead us to a value of VUD equal to 175 kilonewton. So this is the value VUD, we have shown it here. So we can see it here. So we say that this shear force is the target figure for our shear resistance. We want to resist a shear of 175 kilonewton if we can provide sufficient resistance, that VUR. So if you provide a VUR greater than this 175 kilonewton, we will say that the design for shear is complete. So this is the first step of the problem. Now we proceed for the second step. The second step is like this. In the second step, we have to check this value of 175 kilonewton VUD for tau C max. This we have seen in the earlier video, again with details. We will apply it here. What is this check for tau C max and what is its necessity? Its necessity is that the concrete at in this region, support region, is going to resist the diagonal compression developed due to the shear. You know that the shear is going to cause diagonal tension as well as diagonal compression, out of which the diagonal compression will be resisted by concrete, but concrete will be able to resist the diagonal compression if the stress developed due to this shear force is within limit. So we have to calculate the stress this shear force will be developing inside the beam. That stress we will call as the nominal shear stress, tau V. IS code is calling it as tau V. What is tau V? Tau V is VUD upon BD. What is the concept of tau V? It is the nominal shear stress, that means the shear stress developed by the shear force VUD at the critical section. So we will just calculate the shear stress from the shear force. We know that stress is force upon the cross-sectional area. So this shear stress, this is called as nominal shear stress. So VUD upon BD. VUD is 175 into 10 raised to 3 upon 230 by 500. So 230 by 500 is the effective cross section. If you calculate, this will come out to 1.52 Newton per mm square. 1.52 Newton per mm square is the value of shear stress developed at the critical section. So we have to now check that our value tau V, which we have calculated as 1.52, it should be less than tau C max. What is the second value, tau C max? It is the standard value given by the IS code, which we have to follow for this check. Now how to get the value of this tau C max? It will be obtained from table 20 of the code. We have to refer to table 20 of IS code. Here we will be putting the extract of table 20 for our reference. This is IS 456-2000 page 73. The same value, the same table has been reproduced here. Table 20, maximum shear stress tau C max Newton per mm square. It's a simple table in which you have to see the concrete grade that you are using. Let us see what is the concrete grade we are using. You can see in the data we are using M25 concrete grade. So in this table, for M25 concrete grade, you see this tau C max value in Newton per mm square as 3.1 Newton per mm square. So here we are getting different values of tau C max for different grades of concrete. For us, this M25, this value tau C max happens to be 3.1. So we are taking that value 3.1 Newton per mm square from table 20. So now we will compare whether our tau V 1.52 is less than tau C max 3.1. Yes, it is less than 3.1, and that is why we can say that this value tau V is less than tau C max, and hence we will conclude that this check is okay. This check is okay means we are safe now for diagonal compression, and we are safe to proceed for the next step of our design. Suppose in some other problem, when you calculate the value of this tau V, and suppose it happens to be greater than this tau C max, it means that your shear stress developed at the critical section is greater than the permitted stress. In that case, you have to stop the problem of shear design here itself, and you have to go back to the flexural design of beam, and you have to revise the design, so that finally again when you come to step 2, you get this check tau V less than tau C max. So this was an important check to proceed further. So with this step 2, we have taken care of diagonal compression, and now we will proceed for developing shear resistance VUR for diagonal tension. So let us proceed. Here we see the expression, the relation, mathematical equation which gives us the split up of the VUR or the shear resistance to be developed through design. We are going to develop the shear resistance through 3 sources. First source is concrete itself. Second source is minimum shear stirrups, and the third source is bent up bars. So we are going to collect this shear resistance VUR from 3 sources, and we will go one by one. First of all, we will see VUC and check whether that shear resistance is greater or less than this. If required, we will proceed for VUS minimum. If further required, we will proceed for VUB, and like this our design procedure will go. So let us start first of all with VUC. We are not providing any extra concrete for shear. The concrete which is already available, we are using it for resisting shear. So that is why let us first of all find out how much shear force our existing concrete will be able to resist. So step 3 is about that, calculation of ultimate shear strength of concrete. That means ultimate shear force resisted by concrete, and IS code is calling it by symbol VUC. U for ultimate, C for concrete, V for shear. Now how to calculate VUC? IS code is giving a simple handy formula. As per IS 456-2000, VUC is equal to tau C into BD. Tau C is the value which is new in this formula. Otherwise, this BD are the dimensions as we already know. So the value of tau C is to be taken from table 19 of the IS code. So we have to refer to table 19 of IS code to calculate the value of tau C. Just as we refer to table 20 of IS code for tau C max, we will refer to table 19 for value of tau C. Now we will proceed. This is the extract of IS 456-2000 table 19 page 73 of IS code. If we look here, we will see that there are 2 columns in table 19. The first column is the quantity 100 AS upon BD %. So we have to calculate this quantity for our beam, and for that quantity it will give us directly the value of tau C for concrete of grade M25. You have seen this table in the earlier video at full length. I have taken only one column, that is for M25 concrete. Similarly, there are other columns for M20, 25, 30, 35, 40 and so on. So in this video we are taking only the relevant part of that table. So this is one column and this is the second column. Now if we want to calculate tau c for M25, IS code is saying first you calculate this value for your beam. What is this value? 100 AS upon BD in percent. Let us go back and calculate this 100 AS upon BD. Now here, as we saw in the earlier video also, that the value of AS is to be calculated with care. The value of AS, area of steel, is the value of area of steel available at bottom at the critical section or at the face of the column or support. It is not the area of steel available at the center. If you look at these two sections, we find that we are having 3 bars available at the center of the beam, whereas we have got 2 bars available at bottom at the face of column section where shear is critical. So IS code is saying you don't talk about those bars which are at the center, you talk about the bars which are available at bottom at the face of the column or at the support where shear is maximum. So this AS is in this problem 2 bars. At the support we have got 2 bars. Why we have got 2 bars instead of 3? Because we have already bent 1 bar up, and that is why we are getting 2 bars. Now the decision of 1 bar to be bent or 2 bars to be bent is to be taken initially. So here in this third step only, we are assuming that 1 bottom bar is bent up to resist shear. How do we decide that 1 bottom bar is bent up? Now there are 1 or 2 criteria for deciding how many bars you will bend. First thing, you must continue at least 2 bars at the bottom in the support. So your beam is right now having 3 bars at center. If you had only 2 bars at center, you were not allowed to bend any bar in the beam. You have to forget about bent up bars if you are having only 2 bottom bars. Because we have got 3 bottom bars, we can think of bending 1 bar. Because 2 bars must continue at bottom in the support. So we have no choice than we have to bend, we can bend only 1 bar. But remember that if you have got 4 bars or 5 bars at bottom in some other problem, you can bend 2 bars, 3 bars also, except that you have to continue at least 2 bars, that is the condition. But there is usually no point in bending more than 1 bars. You can take advantage of shear bent up bars only due to by bending 1 bar, as you will see in the next step. So you will usually bend only 1 bar and not 2 or 3 bars, even if that is possible in that problem. So assuming that 1 bottom bar is bent up to resist shear, steel continued at bottom at support will be 2 bars of 25. So here we have stated it clearly. Hence PSB, percentage of steel at bottom, will be 100 into ASB into BD. So just carefully observe this calculation. This is 100 into ASB. Here we have taken 2. 2 means 2 bars continued at the support and not 3. So 2 into pi by 4 into 20 square. 20 is the diameter of bar. We have got 3 bars of 20 by diameter or 2 bars of 20 mm diameter. So this, here we have taken the area of 2 bars at the support upon BD. BD is 230 and 500. So this value happens to be 0.546%. This is 0.546%. Now why have we calculated this entire value? We have calculated that value because the table 19 is asking for that value, right? Now let us look at the values here. This table is giving us 0.15, 0.25, 0.5, 0.75, 1 and continued here after also. I have taken only a small part of the table which is relevant to our problem, but the entire table you can see in the S code itself. So we find that it is giving some fixed values as 0.5 and 0.75 for IS for 100 AS upon BD. Our value is 0.4546. So that value lies between 0.5 and 0.75. It is not directly mentioned. I have mentioned only 0.5 and 0.75. So what we have to do is we have to interpolate linearly. So we have to do linear interpolation for value E that we are calling, that is 0.456546, and for that we will get this value of tau c, that is f. So this is a matter of interpolation, linear interpolation. Whenever you are using any tables to find out the values of some variables, we are always required, table is giving some fixed values. If your value is corresponding value is in between those given values, we have to do mathematical, that is linear interpolation. In the earlier video, we have given enough time to uh, explain what is and how to calculate that interpolation. Here I am using it. You have to simply use this formula. You want the value of f. Value of f means value of tau c corresponding to this value of 100 as upon bd. So I have given a, b, c, d, e and f. 6 variables are here. I have shown what is a, what is b, what is c and what is d and so on. And here is a formula. In this formula, you have to put a, b, c, d and e, all the values on the right hand side. Once you substitute all these values, you will get the value of f by substituting these values here, and you will get it as 5.504. In the earlier video, we have done this problem. This is another example. So I am not explaining how to substitute the values and all that. You can pause the video here. You can do the calculation yourself, can confirm, and then proceed further for watching the video. So this was the value f 0.504, which is the value of tau c for concrete grade M25, corresponding to this value of 100 as upon bd. So hence, by interpolation from table 19, that means by doing this exercise, you get tau c equal to 0.504, that is this f 0.04. And that is 0.04 Newton per mm square. The table is giving the values of tau c in Newton per mm square. So you just put this formula, VUC equal to tau c into bd. So tau c into bd is 0.04 into b into d. So this gives us 57.96 kilonewton. 57.96 kilonewton is the value of VUC, which now means that concrete is going to provide a shear resistance of 57.96 kilonewton. 57.96 kilonewton. So out of this VUR, one component is calculated as 57.96 kilonewton. Now let us check, is that value sufficient? We want to resist 175, that is VUD. 175 is to be resisted. Out of that, concrete is resisting only 57.96. So this means that concrete alone is not sufficient to resist this VUD of 175 kilonewton. Concrete is taking share of only 57.96 in resisting. This means that we will have to go for the next option of shear resistance. So we will now proceed. So this is how the problem proceeds in itself. When you compare the value, you are immediately convinced that no, you will have to go to step 4. You will have to go for the next source of shear resistance. So let us go. What is the next step? Step 4. Step 4 is calculation of ultimate shear strength of minimum stirrups, that is VUS minimum. We have seen already in the earlier video that we have to provide some shear stirrups in minimum quantity. Whether required or not, we must provide in a beam shear stirrups. Here we have not designed the beam, so you see this beam without any shear stirrups drawn. Actually, this is never the picture of a beam because you always have some shear stirrups in the beam. Whether required technically or mathematically or not, IS code has compelled us to provide some minimum shear stirrups. So the reasons are already explained in the earlier video. So minimum stirrups are must and they must be provided. So why not take the advantage of their shear resistance? So here we will take the advantage of that minimum stirrups, what shear force they are resisting. So ultimate shear strength of minimum stirrups. We are calling that shear resisted by minimum stirrups as VUS. U stands for ultimate, S for stirrups, and minimum for the minimum stirrups. Now according to IS 456-2000, it is directly indicating us that VUS minimum is equal to 0.4 into BD. There is no question of referring to any table like tau C max or tau C for table 1920. Don't refer to any table. Directly you just get this value 0.4 into BD. So it's 0.4 into 230 into 500. This gives you a value of 46 kilonewton. This means that whatever minimum stirrups you will be providing in the beam, they will be resisting a shear force, ultimate shear force of 46 kilonewton. So this means that now we have got this second value also. So our shear resistance up to now has become VUC plus VUS minimum, right? Two things. So here we will calculate it. Hence VUR, that is shear resistance, now it is equal to VUC plus VUS minimum. So that will be this 57.96 and this 46. So the two added, we get a shear resistance of 103.96 kilonewton. 103.96 kilonewton. Addition of these two sources. Now let us check. They are together giving us shear resistance of 103.96, but we want to resist shear force of 175 kilonewton. Step 1 is telling us always how much you are supposed to resist. So 175 is to be resisted, and we have resisted only 103.96 by two sources together. This now means that as VUR 103.8 is still less than this VUD 175, this is indicating us that minimum stirrups are not sufficient. Minimum stirrups are not sufficient. Even if you provide minimum stirrups with concrete, they are not going to serve our purpose fully. Then what is the next source? We have to go for the third option. The third option is necessary according to this check we have taken. So next step is necessary. You have to take advantage of this bent up bar. So let us take advantage of bent up bar. Hence, so we are saying hence try bent up bars. We don't know whether bent up bars are also going to be sufficient or not, but they are now going to be useful. So we will say hence try bent up bars. So that gives us to the next step, that is step 5. This is how one step gives birth to the next step depending upon this check at the end of every step. So step 5 is ultimate shear strength of bent up bar. So now we have discussed right now that one bent up bar is provided. Now we want to find out how much shear it is going to resist. How much shear force it is going to resist, so that we can put that add object value here. Now IS 456-2000 is giving us a formula for VUB also. VUB means ultimate shear force resisted by B means bent up bar in this case. So IS code is giving this formula. VUB is equal to least of, means smaller of two values. First value is VUD minus VUC, both of the values we have calculated, VUD and VUC, upon 2. And second value is 0.87 Fy N AB sin alpha. This is a small formula as code has given. So you have to calculate this value, you have to calculate this value, and you have to take the smaller or the least of the two values. So we substitute the values here. VUB is equal to least of 1. You put the values VUD 175, VUC this 57.96 upon 2, and the second substitution is this. What is this? 0.87 Fy. What is Fy? Fy is the grade of steel that you are using, Fe 415. So Fy is 415 in the grade of steel. So we have to, this bent up bar is having grade Fe 415 steel. So we will put that 415 here. Into 1. What is this 1? 1 stands for this N. N is number of bars you have bent up. As we said, we have bent up only one bar here. So this N is to be put as 1. Then 314 is AB. A is area of steel and B is bent bar. So what is the cross-sectional area of bent up bar? One bent up bar. It is cross-sectional area pi by 4 into 20 square. Area cross-sectional area of one bar of 20 mm diameter is pi by 4 into 20 square. So if you calculate that value pi by 4 into 20 square, it will come out to be 314 mm square. So this is the value of AB into sine alpha. Alpha is the angle of inclination of this bar at which we are bending it. So this is 45 degrees. So we put this as 45 degrees. So this is how we substitute the values in this formula. So once we substitute and calculate, we find that VUB is least of, first value happens to be 58.52. You calculate it, you get it this way, and you calculate the second value, you get it 96.57. So you see that obviously this first value is smaller and this second value is bigger. So you have to choose the smaller or the least value of the two, and that is why you have to take 58.52 kilonewton. So in this formula and looking at these two values, it becomes quite clear that this second formula gives us a very big value. If you have, and the first formula gives a lesser value usually. And IS code has said that you don't use this value, you use the first value. IS code seems to be conservative about allowing us the bent up bars to resist the shear. It is allowing, but it is putting a condition that you should choose the smaller value of the two. And that is why it is not worth going for n equal to 2 or 3, because this value for one bar also it is so high than this value. There is no point in increasing the number of bent up bars. So we are getting this final answer as 58.52 kilonewton. So the bent up bar is now resisting 58.52. Look here, again going back. So now we have got all the three values. Let us add them. So now VUR, this VUR now it is equal to three values. So put these three values. VUC is this value, VUS minimum is 46 as we have seen, and VUB as right now calculated 58.52. If you add all the three values, you get 162.48. It was 103.96 earlier. It has increased by due to this bent up bar to 162.48, and that is our resistance now with these three things. Now let us check whether it is correct or whether it's sufficient or not. So it's what, how much we want? We want 175. VUD is 175 and we have got only 162.48. Again, it is still little but less than 175. So we see here that VUR, which was this 162, it is still less than VUD, and we find that the conclusion of this step is bent up bar is also not sufficient. Minimum shears were not sufficient, so we went for bent up bars. We calculated and we find now that bent up bars are also not sufficient. I hope you understand this stepwise progression of the solution of the problem and how we are going to the next step and next step by just through the same steps, earlier step. So here we have to understand that bent up bars are not, one bent up bar or bent up bars are not sufficient. Now what is to be done? This is the question. We had got three sources of shear resistance. We used all the three and we found out that our shear 175 VUD is not resisted fully. Then what is to be done? There is no fourth source. Only three sources are here. In that case, we have to give a rethought to all the same three sources here. We cannot do anything to this VUC. We cannot increase VUC by any way. We cannot increase VUB also by any way. We can only make a change in VUS minimum or VUS. We have taken minimum stirrups here. We were assuming that our beam will be happy with minimum stirrups. But now we say that we cannot be happy with minimum stirrups. We need some extra stirrups. We need some additional stirrups than the minimum stirrups. The provision of shear stirrups is in our hands. Though VUC is fixed, VUB is fixed, this VUS minimum can be increased to some maximum value, some additional value. So what we will now do is, instead of using this VUS minimum, we will replace this VUS minimum by VUS only, not minimum. We will remove that minimum and we will increase these shear stirrups, right? How much, by how much quantity we will increase this stirrup and all that we will see in the next step. But we will have to increase the stirrups than the minimum stirrups. That means we will have to design extra shear stirrups. We will have to design extra shear stirrups, and that is what tells us this, that hence design shear stirrups near the supports. So we come to this step 5 with this conclusion, that in the next step we will be designing shear stirrups higher than this VUS minimum. So coming to step 6, design of shear stirrups near supports. So we will be now designing the shear stirrups. To design a shear stirrup means to do what? We know that a shear stirrup, we have seen in the earlier video different types of shear stirrups also, and we have also seen that a typical and commonly used shear stirrup is a two-legged shear stirrup. This is a single bar of steel which is bent at the corners like this, and finally there is a hook at the end. So this is a single bar bent to this shape, which we call as shear stirrup. Now it is having two legs, the vertical portions, and this red crack, diagonal tension crack, it is shown. So it is cutting the two legs of the shear stirrup, and that is why we call this as a two-legged shear stirrup. Now to design the shear stirrup means to do what? You have to first of all decide the diameter of bar which you are using for this shear stirrup. Secondly, grade of steel of that bar, and third thing, the spacing of the shear stirrups that you are going to provide. All these three things will depend upon how much shear force these stirrups are supposed to resist. The spacing of the shear stirrups will depend upon how much shear force are you supposed to resist. If you want to resist a smaller value of shear force, you will require a larger spacing. If you want to resist a greater value of shear force, greater the value of shear force to be resisted, closer the spacing of the stirrups. So the shear stirrup spacing will depend upon the value of shear force you want to resist. But before that you have to decide the diameter and the grade of steel. So we will here say try two-legged 8-5 stirrups of Fe415 grade steel. Here we are saying try. Try means with this assumption we will proceed. So we can usually start with this assumption that we will use two-legged stirrups, that is almost universal. Then we will use 8 mm diameter bar for making a stirrup, and we will use the stirrup of Fe415 grade steel. That is what is the grade of steel that is given to us. So we will assume these three things: two-leg stirrups, 8 mm diameter, and Fe415 grade steel. After assuming these three things, what is left is only the spacing of the stirrups. So the spacing of the stirrups will be calculated from the amount of shear force you want to resist. The spacing will be dictated by the amount of shear force that you are supposed to resist. So here we will first of all, this formula is given by IS code. Spacing of shear stirrups, SVS, S for spacing, V for vertical shear stirrups, and S is for the stirrups. So SVS, the formula is 0.87 Fy into ASV into D upon VUS. What is this VUS? This VUS is the shear force you want to resist by using these shear stirrups. You will see that VUS is in the denominator. So as greater the value of VUS, smaller will be the value of spacing. So the spacing will be obviously inversely proportional to the shear force that is to be resisted, which means that greater the shear force to be resisted, closer the or smaller the spacing of the shear stirrups. So first of all, let us find out how much shear force do we want to resist. So we have to go back to this calculation of the earlier steps. Finally, we want to resist 175 kilonewton shear force. But out of that, 157.96 is already resisted by concrete and bent up bar are resisting 58.52. Minimum stirrup were resisting 46, but now we are not using these minimum stirrups because we found in the earlier step that they are not sufficient. So we will remove this minimum stirrups and we will provide higher value of shear reinforcement. So these two values are already there. We need not provide stirrups for these two, VUC and VUB. So we want to design the shear stirrups for a value 175 minus this VUC minus this VUB. Remaining value of shear force will be used for designing the stirrups. So here we get VUS. VUS is the shear force we are expecting for the resistance through shear reinforcement. So VUS is 175 minus this. Here you get VUS equal to VUD. This is the formula we get, and that formula, if you understand the logic we use, this formula is very simple to understand, and this gives us a value of 58.52 kilonewton, which means that if we remove this VUS minimum, we will require 58.52 kilonewton to be resisted by shear reinforcement. So we will put the values, and spacing required for this design shear stirrups is SVS. We are calling it as SVS. That is equal to 0.87 FYSV. That formula is there, which we have stated here earlier. I will now substitute the values. Now you have to pay attention while substituting the values. 0.87 as it is. Fy is 415. What is Fy? Fy is the area, the grade of steel of this particular stirrup. Okay. You have a choice of using different grade of steel for stirrups also. This Fe415 was for the bottom bars, tension bottom bars of 20 mm fine. You could use a different grade of steel for the stirrup also. But in this right now we are not using a different grade and we are using the same grade. So that Fy is 415 into 100. What is this 100? This 100 is ASV. What is ASV? ASV is the area of cross section of the two legs. So area of cross section of one leg is going to be 8. Here you can see ASV is 2 into pi by 4 into phi s. Phi s is diameter of stirrup bar. The bar you are using, the diameter of stirrup bar, we are taking 8 phi stirrups. So this is 8 square, and we are using 2 legged stirrups. So we are getting this 2 here. Okay. If you are using in some other problem 4 legged stirrups or 6 legged stirrups or 3 legged stirrups, you can have this value of 2. Instead of this 2, you can get accordingly 3, 4, 5, 6, whatever. But as we know that the other types of stirrups are not commonly used, the most common are this. So 2 leg stirrups. So this 2 stands here. So you get this ASV as 100 mm square. So we put that 100 here. So this is ASV 100 into D. This D is 500, the effective depth of the beam given, upon VUS. VUS, as we have seen here, 58.52 into 10 raised to 3. To take care of units, you have to use this 10 raised to 3 and so on. So finally you get SVS equal to 308 mm. SVS equal to 308 mm. That is the spacing of stirrups which you need to provide. Now this spacing of 308 mm is not the final value of spacing, because IS code is putting 2 conditions on this value. So IS code is saying first you calculate that SVS by this formula, but don't make it final. You have to check this value. What is that check? Check for spacing of stirrups. Okay, check for spacing of stirrups. IS code is saying that your spacing, whatever spacing you get, it should not be it should not be greater than 300 mm. It should not be also be greater than 0.75 D, right? So what you have to do is you have to calculate this value 0.75 D. So how much it will be? 0.75 into D is this 500. So you will get 375. So IS code is saying that whatever final spacing you want to provide, it should not be greater than this 375. We have got 308, so it is not greater. It is also saying the second value as 300 mm. So it says that in any case, spacing of stirrups should not be greater than 300. Whatever you get from your calculations. So from calculation we have got 308. So what practically or simply we have to do is, once we get this value of SVS, you have to calculate the other two values 0.75D and 300, and you have to take the minimum of those three values, right? So 0.75D is 375, this is 300, and the third value is 308. So this means that out of these three values, 300 mm is the minimum value, and that is why we will finally provide SVS as 300 mm center to center. What is the meaning of this? The meaning of this is that in order to resist a total VUD of 175, concrete is providing this much resistance, VUB is providing this much resistance, and the remaining resistance of 58.52 will be provided by designed shear stirrups when you place 8-5 stirrups of Fe415 grade steel at a spacing of 300 mm center to center. So by this stirrups of 300 mm center to center, you have satisfied the condition that VUR is greater than VUD. So shear resistance is fully developed to resist this VUD. That means that by providing these stirrups, this bent up bar and this concrete, your design of the beam will be over for shear. So theoretically or numerically, the design for shear is over with this. Now, here we come to a next point, the last and next point, that we need to do one more thing, because providing this 300 spacing and this increased additional shear stirrups, in addition to this VUS minimum, we are providing all this. So that is not necessary for the entire 6 meter span of the beam. This is the next point. What is this next point? This step 6 is giving us a spacing of 300 mm. Now the question we are asking is this 300 mm center to center spacing necessary for the entire span of the beam? The beam is having span 6 meters. So for a 6 meter span at 300 mm center to center, you are providing these stirrups. Now the question is this designed shear reinforcement necessary for the entire span of the beam, or is it required for only some support portion of the beam and elsewhere the minimum stirrups will be sufficient? That is the question. Now this question is to be answered by using the shear force diagram. Let us look at this shear force diagram. Actually, theoretically, the design is over here itself, because you have provided VUR greater than VUD. But now we are going one step ahead to achieve economy. From our design. Are we providing unnecessarily large amount of shear reinforcement throughout the beam? Should we restrict it somewhere? So that is what we are saying now, right? So we are going for one step ahead just to achieve economy of providing shear stirrups. Now let us see the logic behind this. We know that this is the beam given to us having UDL simply supported beam, and we are conversant that this shear force diagram for the beam is like this. You are having maximum shear force at the supports, that is, and we are now calling it as VUD. This is 175. It is maximum at the supports, but it is not constant throughout the beam. In fact, it is only maximum at the support region, and it goes on reducing linearly to the center, to the extent that at center you are getting zero shear force. The shear force is zero at the center, and it is again increasing and becoming maximum at the other support. What we have done in the design is we have taken this extreme value 175 and we have calculated these stirrups. And now we are saying that we will provide these stirrups for the entire beam. So that is actually theoretically not necessary. Wherever the critical section was there, these spacing and these stirrups are necessary. So we will consider one intermediate section here. What is this section? This is the section at which these minimum stirrups will start. The minimum stirrups will be enough for the middle zone. So now what we will do is we will divide this span of the beam into zones. We will have a middle zone. This middle zone in the shear force diagram is telling us that middle zone is the zone where you can be happy with the minimum stirrups. The beam can be safe even with the minimum stirrups because the shear force has reduced, and that reduced shear force is VUC minus VUP, and you can provide minimum stirrups for this middle zone. Now for the zone which is close to support, this zone is L1 and this zone L1 from the other support. You need the designed shear stirrups of this space. So whatever shear design we have done, that shear design need not be applied for the entire beam as it is. That will become uneconomical. We will be providing unnecessarily extra stirrups for this middle zone where minimum stirrups were sufficient. So this will lead to uneconomical design. That is why we are dividing this beam into the zone L1 and the minimum stirrups. So let us note that what is this L1, length L1. So if you look at the two triangles, this bigger triangle, the smaller triangle, and symmetry of those triangles, by simple geometry you will be able to find this formula. What is this formula? L1. Formula is giving us the value of L1. What is this L1? L1 is the zone or the part of the span of the entire beam in which you will be providing stirrups at 300 mm center to center. These 8-5 Fe4 and 5 stirrups. Otherwise, in between you will be providing minimum stirrups. Okay. So this is how we have divided the beam into two zones. Zone of minimum stirrups and zone of maximum stirrups, that is L1. So these are the two zones of the beam, and we have divided the beam into the zones in order to achieve economy. Now you will calculate this value of L1 by using this formula. So let us proceed for step 7, which is the zone of design shear stirrups, that is L1. This is the zone of design shear stirrups, and this LM is the zone, middle zone of minimum shear stirrups. So the length of designed stirrups zone L1 is given by L. This formula you have to use directly. If you substitute the values VUD, VUC, VUB in this formula, you will get this L1 equal to 1 meter. If you do the calculation, you will get 1 meter. What does it indicate? It indicates that those maximum stirrups, extra additional stirrups, or the increased value of stirrups was required only for 1 meter span of the beam from the support. 1 meter from this side and 1 meter from this side. The remaining 4 meter, majority of the span of the beam, the remaining middle 4 meter, you can use only the minimum stirrups. You need not spend any more steel for this. So this is the advantage this zone distribution is giving us. So we have calculated that this L1 will be 1 meter. It means now that in this 1 meter we will provide 8-5 stirrups at 300 mm center to center. Now in 1 meter, that means in 1000 mm, how many stirrups you will get? What is the number of stirrups you can get at a spacing of? So this 1000 mm distance is to be divided by 300 mm, and you can see number of designed stirrups N1 will be equal to L1 upon SVR. right? So this SVR which we have, or SVS actually we should say, SVS. So this SVS will be 1000 upon 300. So this is 1000 is L1 upon 300 is the spacing. So this gives us to 3.33. So it is obvious that it is not possible to provide 3.33 number of stirrups. So we will round it off to 4. So it means that you have to provide 4 stirrups in this zone, equidistant 4 stirrups. That is easy on the site. Instead of telling the spacing on the site, you may provide that it is 4 stirrups, right? So 4 stirrups you will be providing. So this is the conclusion, that the design stirrups will be provided 4 stirrups in this zone, Now in the middle zone, you will be satisfied with the minimum stirrups. Now you are saying minimum stirrups, but the question is, minimum stirrups means how many stirrups? Minimum stirrups means how many stirrups? So for that you will have to calculate the spacing of minimum stirrups also, in order that the site person can provide the stirrups at that distance. So we will now proceed for calculation of spacing of minimum stirrups. We calculated the spacing of the designed stirrups like this. Using the same formula, we will be calculating the spacing of minimum stirrups. But to calculate minimum stirrups, again we will have to decide the diameter of stirrup bar and the grade of steel, right? So these are 2 different sets of stirrups. So this second set of stirrups in the middle zone is the minimum stirrups. In this problem, we will provide 6 mm diameter minimum stirrups and Fe 250 grade steel bar for that, right? So here we are using a different grade of steel as well as a different bar diameter. This is for academic purpose. We are taking all possible complications of the problem in the same thing, so that you get absolutely clear about all the concepts of shear design. So we have a choice. A designer has a choice. Should he take 6 mm bar, or should he take say 8 mm bar? What grade of the steel he should use for the stirrups? He has to finally take care of the checks of spacing, but he has got the choice of choosing the diameter of bar as well as of the grade of steel. So let us try 6 mm Fe 250 grade steel for minimum stirrups. Then in this formula you get Fe 0.87 Fy ASVD upon, this is going to be what now? This is going to be VUS minimum, right? Here these symbols are playing very important role. So this is going to be VUS minimum, because we are now designing the spacing for minimum stirrups. So let us see how the substitution goes. 0.87 into Fy. Now remember or see that this Fy is now 250, because you are using Fe 250 grade stirrups, into 56. What is this 56? It is ASV. Again it is a 2-leg stirrup, but the bar diameter of stirrup is 6 mm. So 2 cross section of 6 mm will give us 56 mm square. Just as this has given 100 mm square, we will get 56 mm square here. This D is 500, the same thing, upon this is VUS minimum. VUS minimum is 46. So we are getting this VUS minimum as 46 into 10 raised to 3. So this amounts to 132 mm. So this is the spacing of the minimum stirrup zone stirrups. So 132 mm. So we will round it off to 130 and provide a minimum stirrups of 6 pi at 130 mm center to center in the middle zone. Now similar to this, we have to again apply check for spacing, but we see here that the check for spacing is that 3 and should not exceed 300 mm. Our spacing is much less than 300 mm. So this check is automatically obtained and we get this as the spacing for the stirrups in minimum stirrups zone. So friends, in the last step or up to the last step, we have completed the design numerically, design of the beam for shear. And by taking care of economy, we have divided the beam in 2 zones and we have provided different sets of shear stirrups in the two different zones. Now in the last step here, we are going to see the reinforcement detailing and drawing. That means whatever design calculations we have done, in order that they are actually implemented on the construction site, we have to convert all these design calculations and conclusions into drawing, and that is why we will be seeing how to draw and what is the reinforcement detailing and drawing. So there are 4 points in reinforcement detailing and drawing. You can see this drawing. This will be a drawing which will be sent to the site as a conclusion of this problem. Now, first point, provide shear stirrups in two zones. There is a 6 meter long beam. This is a half part of the beam. We are now telling that you divide the beam in two zones. You are saying that you have to provide 4 stirrups of Fe415 grade steel of 8 mm diameter at 300 mm center to center. This is what we have concluded in the previous step. Now that we are putting as a conclusion. So you can see here. Here is the span of the beam. Here you see zone 1, 1 meter distance, and here you see 4 stirrups. 1, 2, 3, 4. 4 stirrups. Here the labeling is there. #4 means 4 stirrups of 8 mm far diameter at 300 mm center to center. So this spacing is 300 mm center to center. We are calling them as designed stirrups. They are made up of Fe415 grade and they are provided near both the supports. At this support, similarly at the other support. So this is about zone 1. Now what about the remaining portion, middle portion? Zone 2. We are mentioning it clearly in the middle zone. We will provide minimum stirrups of Fe250/6.5. So just see here. All these stirrups, they are appearing to be very close to each other. Their spacing is 130 mm as against this 300 mm. But these are the stirrups of smaller diameter and they are the stirrups of the lesser grade of steel. That is why we find that the stirrups which are minimum are closer and the stirrups which are more than minimum are not closer to each other as compared to that. So this picture appears to be reverse or appears to be paradoxical, but in terms of spacing only. But if you look at the bar diameter and the grade of steel, it is obviously justified and understandable. So we see that these are the minimum stirrups of Fe250 grade in the middle zone at a spacing of 130. So this is 300, this is 130 spacing. Roughly proportionate drawing is expected. It is not to be drawn absolute scale, but they are to be roughly proportional. So this is zone 2 and we are seeing this one bent up bar. So this was the first part of the conclusion. Second part is you have to mention on the drawing that one bar of 20 mm bottom bar shall be bent up at a section from where that bar is no more needed to resist flexural tension. That is, you are not supposed to tell this theory on the drawing sheet. Finally, you have to conclude that is, say, at a maximum distance of 2d, 2 into 500, that is 1000 mm from the center of support. You have to mention the exact point at which you are supposed to bend the bar. Otherwise, the person on the site is illiterate. He will bend it at any point and that will create problem. We want to bend the bar where it is no more required for resisting the flexural tension. So we have to bend it at a distance 2d in this case. If you are bending one bar out of 3, that bar is to be bent at 2d from the center of the support. So this distance at which it is bent, it is supposed to be 2d from the face of support. That is the second point of conclusion of design. The third point of detailing is that provide 2 anchor bars, 2 at 8 mm far. So look at these 2 anchor bars. We have been given only these 3 bars and we have designed the shear stirrups. These top bars, these are called as anchor bars. They are randomly provided as 2 bars of 8 mm, that minimum bar diameter, to support the stirrups. So these top bars, they are additional bars which are called as anchor bars, and their purpose, they are secondary bars. They are not supposed to take any compression or tension. They are not structural steel, they are non-structural steel or secondary steel, and their purpose is to hold the stirrups, to support the stirrups, so that the top anchor bars, the stirrups and the bottom bars, they provide a firm skeleton and the bar spacings are maintained properly. So that is why we provide these two anchor bars. So they are not to be theoretically designed, they are to be randomly provided as the minimum 2 bars of 8 mm diameter. So these are the top bars. That is why we have shown them by different color. They are non-structural bars, they are not taking any tension, they are not supposed to take any tension or compression. So that is the detailing here. So you see this entire reinforcement detailing here as given here. Now the last point in the reinforcement detailing is that the first stirrup, these stirrups, they have to start from the face of the column. You cannot insert this wrongly. Many times the drawing is then made that this first stirrup is shown inside the beam, or they may be showing sometimes it is at the end of the beam. So that is not technically possible. Let us see this picture in which we see 4 beams meeting at a column, a junction, and reinforcement is exposed. Concrete is not done up till now. These are the vertical bars of the column, and these are the stirrups of the beam. This beam, look at this beam. So this is the first stirrup of the beam. Now you can imagine if you put this stirrup inside the column, is it possible? It is not possible to insert your stirrup inside the column. So you have to provide the first stirrup at the face of the column. This is the face of the column. When concreting will be done, this will become the face of the column. So this instruction is given. The first stirrup near either support or each support shall be provided at the inner face of the column. So that instruction is important, and the students have to take absolute care while preparing the drawing that they should not insert this stirrup inside the column. So this was all about the solution of the problem, and it ended with the reinforcement detailing. Now in conclusion, we will go for some variations in the problem. The problem is over in all respects. Now in some other problems to come, you can get little variations so that you can solve all the problems, all possible problems of this type. We are now considering these possible variations of the problem. The same procedure and same logic will be used for all the problems. The possible variations are like this. First variation is the problem, every problem may not have these 8 steps. As we have seen, some problems may end at 3rd step or 4th step or 5th step, depending upon the VU and VUR and VUD comparison. So depending upon your problem may not require bent up bars. In your problem only minimum stirrups may be sufficient. So like that your steps will depend. Secondly, other diameters of stirrup bars can be used. As we already saw that bar diameters of stirrup bars are to be assumed by according to the decision of the designer. So we used 8 mm stirrups as well as 6 mm stirrups in this problem. Some other designer may use all 8 mm stirrups. Some other person may use all 6 mm stirrups. Accordingly, he has to go ahead. Also, the grade of steel for stirrups is also to be decided by the designer, and accordingly he has to take care of the specifications about checks for spacing. That is what IS code is saying. Now the third point is bent up bars may not be used. Some designers prefer that bent up bars are not used at all. Whether they are useful or not, they don't want to use bent up bars. Maybe for the reason that bending a bar is a tedious thing on the construction site, and there are possible errors also about the distance at which the bar is to be bent, also the angle and so on. So some designers have a style that they don't use bent up bars. They use all stirrups to resist shear. They don't use the contribution of bent up bars. Whereas some designers feel that bent up bars also can be used so as to achieve economy. It is all the choice of the designer. So in your problem you have to be watchful whether they are saying use bent up bars or don't use bent up bars. Accordingly you have to be careful in reading the statement of the problem. Accordingly, you have to modify your procedure of design. In our problem, we have taken all possibilities. Now the fourth variation is designed stirrups may be provided throughout the span by accepting some uneconomy for convenience. So we said here that we have got these two zones. We provided the stirrups in two zones. And why we did this zoning? We did it for the sake of economy. Otherwise, it was all right to provide all the stirrups of this 8 mm 300 spacing throughout the beam. That would be uneconomical, but that would not be technically wrong. So, if you are ready to accept that uneconomy, then it will be convenient to provide all the stirrups throughout the span, the same spacing, but in that case you have to accept the uneconomy of the design. And the last point is of variation is that this is a fact that Fe250 bars, as we have used here for the mild steel bars for stirrups, nowadays since long actually they are not being used on the construction site. So we are using all the bars of TMT steel in general. So this Fe250 bars, though we have used, IS code is not prohibiting. IS code is not saying don't use mild steel bars. But the current practice is that we are not using them. So that is a matter of information for us. Academically, this is all valid and you can use them. So that was a complete problem of design of beam for shear along with the possible variations in the problem. Now friends, before we close this lecture, there is a formative evaluation self-test. So pause the video and write on a paper the answers of the following questions. First question is, solve the problem 5.3.1, that is the problem which we solved right now, without using bent-up bars. This is an application level question. Second question is a practice oriented question. Visit a construction site and check with the drawing on the site the shear reinforcement of real actual beams on the site, 3 beams on the site. So do this exercise as a formative evaluation. And friends, now we come to the end of this lecture. We sum up. This was lecture 5.3, problem on shear design of beams. The expected learning outcome of this problem was to design a beam for shear. The contents of this video lecture were 1. The numerical problem 5.3 complete solution for shear design of beams. And the second point was variations in the problem. We used some key terms. Shear design, critical section for shear, shear resistance of concrete VUC, table 19 and table 20 of IS 456-2000, minimum stirrups, designed stirrups, stirrup zones, bent up bars, and anchor bars. You contact your teacher for any doubts or queries. You can rewind the video, pause the video at various points and get the concepts clarified. After you have got your doubts cleared, do attempt the summative assessment quiz, which I will be putting in as usual in the Google quiz form, and the link of this Google quiz will be provided in the description section of the YouTube video of this lecture. Friends, we have got our smart friend Smarty with us to say thanks. So, thanks for watching this video. Goodbye till we meet in the next lecture.